And the start of today's lesson reviews what we did yesterday. So yesterday we were rotating things either about the x-axis or the y-axis. We were either using the disk method if it was a solid shape, or the washer method if you had a gap in between and you're doing one function minus another function. And we showed that by having a big radius minus a little radius. Now we're going to extend that by not just doing over the y-axis or the x-axis, but we can do it over other vertical and horizontal lines. And then you can think, well, would mathematicians extend that to rotating something over y equals mx plus b, any line? Could you rotate something over a parabola? Yeah, like the brain can think of what's the next step, and then the math can do that. It just gets more complicated. So find the volume of revolution generated by revolving the region bounded by the square root of x from 0 to x equals 4 about the line y equals -3. So if I draw a little picture, okay, here's the square root of x, okay, and we're going from 0 to 4. And -3. So now this is the solid that we're rotating, instead of just doing the x-axis. Well, whenever you're rotating something with the disk method, this is our radius now. That's what's going to get rotated around. In fact, if I take this distance and make it the same thing here, right? There's my open circle. Right, that's the part of my watermelon right there. I could go 3 here and I gotta color it all in. Can't leave the watermelon without coloring it all. So now our big radius was the square root from before, but can you see we added 3 to it when we extended and rotated it around -3. So now our big radius is just the square root of x plus 3. And that whole thing, because it's pi radius squared, because we make a bunch of circles, now this has to get squared. So we have to do some preliminary math and actually multiply that out. Square root of x plus 3 times square root of x plus 3. Multiply that out and we get x plus 6 root x plus 9. And each of those 3 things you can integrate, plug things in, and we can find the volume. So rotating it around another line just changes your radius. Because our big radius was the square root of x, that only gets us to the x-axis. We'd have to add 3 more. So find the volume of the solid of revolution generated by revolving, and both of these, well, the one equation is x equals, and we're revolving around the line x equals 3. So 1, 2, 3. Here is, I'm going to draw it with the dotted line. Here's x equals 3. That's what we're revolving around. x equals y squared plus 5. Okay, so I should have drawn my graph a little bit better, but x equals y squared plus 5. That's going to be a parabola. It's going to have when x is 0, sorry, when y is 0, x is 5. And it's going off my graph there. Didn't do a really good job of graphing this. And we're going from y equals -1 up to 1, 2, 3, up to 3. So we would have to graph x equals y squared plus 5. And we would want to take that area on this side and rotate it around that graph. So what do we have? We have that our big radius was y squared plus 5, but y squared plus 5 would, like if we have this parabola here, that big radius normally would have been all the way down to here. Does that make sense? And since we're only rotating it about here, now this is the radius part here. We have to subtract the 3 because our rotation thing is closer to that parabola than the y-axis. So you'll notice that sometimes by rotating it around a new line, sometimes you're going to be adding the number if that made your radius bigger, and sometimes you're going to be subtracting that number if that makes your radius smaller. In this case, it makes it smaller. Again, we would have to multiply this out. So I can put the 5 and the 3 together as like terms and have y squared plus 2. FOIL that out, multiply it all out so that I can do my integration. I know that you can plug in the next numbers, so I'm going to cheat and just show you the answer. To save you some time. Sorry about my graph being way off. But look at these numbers. Would you get this on a non-calculator? No. Can we type in x equals y squared plus 5 easily into our calculator? No. Okay. Could you do this on your calculator? If your x's and y's were just switched, would it not be the same question? Like if does it matter what x is and what y is? These are just, this y squared plus 5, x equals y squared plus 5 is just turning our paper sideways and looking at a horizontal parabola. I would switch everything back and make it a vertical parabola and change all my things, and then I could type this easily into my calculator and do things that way. And chances are, well, if the answer was in terms of pi, then you'd have to use your calculator to do the work along the way. But if it wasn't, you could do that kind of switching and figure it out with what you're used to using the x value. Okay, this looks really advanced. Okay, the diagrams look fancy, but it's just our washer method extended to move over different lines. So our washer method was the big radius minus the little radius. Send that around as circles all the way through. Now, if you were going to take, here we have the line y equals 2x and the parabola x squared, and we're now rotating it around -5. Can you see that the 2x is the equation that's on the top? The 2x is going to be your big radius. So my big radius here is going to be 2x, but 2x only gets me to the x-axis. And then I would have to add 5 to get to this value. And my small radius, is the x squared graph, but the x squared will only get me to the x-axis, and then I would have to add 5 to that. So I've got my big radius and my small radius, and then I'm going to put this together. So my volume will be pi. Here's my big radius, 2x plus 5 squared, minus my small radius, x squared plus 5 squared. And of course, you'd have to multiply those out and combine your like terms. You just have to trust me that that's what it works out to. But I know you could do that. Add 1 to the exponent and divide. Those are nice, easy integrals. And we get our answer. So rotating it around a new line either will add or subtract to your radiuses, depending on where that line is. Drawing a little picture can often help us. In this case, does it make sense that my big radius got extended by 5? So did my little radius. And our last question just looks at the same idea of the washer method, but going around the y. Okay? So, first of all, normally when we rotate around the y-axis. So to start with, if I was going around the y-axis, the blue one, this would be my big radius. And the green one, if I was going around the y-axis, would be my little radius. That's what those values would be. Okay? But now, I'm rotating around x equals 2. So my big radius is actually, or my big radius around the y-axis is actually this part there, my small radius. And my green line, and I'll draw it just above, just like I did the other one. Oh, that's not just above. Okay, that's now my other radius. To make this disk right here, I would take the green disk, complete disk, minus the blue disk to get the washer. So now the question is, how long is this line? Because this line is now my big radius, right? And how long is this line, which is now my small radius? Okay. Looking at the picture, and again, drawing the picture, getting a sense for it can tell you what to do. Memorizing, oh, sometimes I add 4, sometimes I subtract 4, can throw you off a little bit depending on the situation. So instead, if I look at the picture and I wanted to find this R, does it make sense that it was from here to here would have been 2, but now I have to subtract, and that blue line was the square root of y. My big R here, again, I'm going to do the same thing. I'm going to start with 2, but now I am subtracting my red line, which was y over 2. Getting the setup is the hardest part. Now the process from now on is the same as we've done all the way through. How do I find the volume? I do pi r squared, I do big radius, which is the green one, right? This is the green one, I'll put a green box around it. Minus small radius, that's the blue one. The blue box around that one. Yes.
This is the same as y over 2 minus 2 squared minus root y minus 2 squared, right?
If you factored out the negative, right? But writing it that way doesn't make sense with the picture. Okay? Yeah, because when you square something, if I flip those two numbers around, one way will be a positive number, the other way would be a negative number. They'll be the same value, like -3 and +3. When you square it, it wouldn't make a difference. They'd be 9 either way. But I write them this way because that's what matches up with my diagram. And when because you'll still have to square this out. So when I square these things out, it would come out to the same thing whether you did it the one way or the other. Here we can combine some of our like terms, definitely would do that. The 4 and the -4 nicely go away. These are all fairly easy integrals. You'd have to remember the square root is exponent of a half, so you'd add 1 to that and divide by 3/2, which I divided by 3/2 and already simplified to get that 8. You could easily plug in those numbers and get 8/8 pi. Let's look at the final shape. That looks like a tent. Makes me want to go camping. It's almost summer, right? It'll be summer in about what, 4 or 5 months? Feels like.
Question.
For some reason, I feel like we should be going from 2 to 4, not 0 to 4. Why are we going from 0 to 4?
We're going from 0 to 4 because these are intersection points and we're rotating around y values.
I guess I was confused because of the arrow on the top.
Like the circular arrow.
Yeah. That's,
It makes you think you're doing X's when you're thinking this way. You have to realize I am drawing these discs starting at the bottom and adding all those discs until I get to the top. In this case, all of the washers from the bottom until the top. It looks like where the disc is right now is when your tent has the most insulation. You could probably, this has enough insulation, you could take this camping this weekend. It's supposed to snow tomorrow.
I thought it was supposed to snow today.
this is so a lot.
A lot?
Yeah, 10 to 30 centimeters.
That's not allowed. That's not fair. Right? Okay. Well, on that happy note,